Hello everyone, I'm Alex Alemi, and I'd like to present our work for the workshop PACm Bayes, Narrowing the Empirical Risk Gap in the Misspecified Bayesian Regime. And this is with my co-authors Warren Morningstar and Josh Dillon, and we're at Google. So we all know Bayesian inference is optimal, so we go home. Everyone, we should be Bayesian. Except there's an asterisk. There's some fine print. Let's zoom in a little bit. Oh, yeah. Bayesian inference is optimal, but only on average if you have the correct likelihood and prior. And I think of all places here at the Your Model is Wrong workshop, I think we're aware of the fact that we don't always have the correct likelihood and prior. And this can have disastrous consequences for Bayesian inference. And in some sense, that's the point of our paper. Bayes fails, and we have a patch. So let me kind of illustrate that. Imagine I have a simple example. Imagine I have some two-dimensional data distribution. Looks like this. It's heteroscedastic. There's more noise over on this side than there's over this side. And let's say we're interested in modeling this. So, what might you do? The very first thing you might try to do is neural network regression, right? We're machine learners, so you build a feed-forward dense net, and you try to do regression. So as a probabilistic model, what are you saying? You're saying that you're going to use a neural network to take each x and output a mean, and then you're going to use a observational likelihood, which is Gaussian, where you take that mean and you have some kind of fixed variance, let's say 1, and you maximize the likelihood. You do maximum likelihood. So let's do that. Let's do gradient descent. Let's set all the parameters of our network, and let's try to model this data. This is what we get. So, the neural network does it. The neural network can kind of model this data. It learns to go sort of right through everything. But what I'm showing here is actually the predictive distribution. Because, we had an observational likelihood that was Gaussian. It was fixed variance Gaussian. And so, the neural network learns to kind of go, right in the middle of all the data. But, our Gaussian, then our predictive distribution has a one variance 1. This is what 1 looks like on this plot, and so there's some predictive likelihood has some uncertainty, but it really doesn't capture the data. It hasn't learned. It can't handle the fact that the data is heteroscedastic because the model was misspecified. Okay, but this was maximum likelihood, right? I mean, this was a single parameter setting for the neural network. This was just a single checkpoint. This was just one neural network. I mean, one neural network with a fixed variance Gaussian can't do anything about this. Okay, but so what do? We want to model uncertainty. Let's be Bayesian. And, in principle, Bayesian could do this, right? Because you instead of just having a single parameter setting, what we're allowed to do in Bayesian inference is specify an entire distribution over the parameters in the neural network, and we marginalize that out to form the predictive distribution. So let's do it. What are we going to do? Let's do Bayesian inference. In fact, let's do variational Bayesian inference. Let's make it tractable. Although the result doesn't matter. Let's do Bayesian inference. What do we get? We get this. Fundamentally the same. I mean, if I switch back and back, it's a little more uncertain. There's a little bit more uncertainty there, but it's fundamentally the same thing. And this is because Bayesian inference is sort of, it's built on a framework that assumes that you have the correct model, and it looks for the best single parameter setting of your model. It really does. It just sort of is a little bit more conservative about that. So it can't fix this problem. It can't. But we got a patch. So to take exactly the same model, take exactly the same likelihood, take exactly the same prior, take exactly the same variational posterior, same optimizer, same number of parameters, same everything. Just change the loss function. Just change the loss function and try to search in the space of your variational posterior with a different loss. And what can we do? We can do this. We can go from failing to nailing this problem. We can go from a model that doesn't capture the heteroscedasticity to one that does, without changing anything except the loss. Let me show you. Here is kind of the loss you would write for variational Bayes, the elbow. And this is our proposed loss, PACm. And I don't really want you to read these, but I want you to notice these look pretty much the same. I mean, operationally, what does Bayesian inference do, right? It takes as input a prior distribution, some likelihood, and a posterior distribution with parameters. And then you sample from the posterior some number of times. Let's say you compute the likelihood of all of those parameter samples. Then there's a KL penalty that keeps your posterior close to the prior, and then you evaluate the average likelihood. You put together the elbow, right? So you look at the sort of likelihood that you achieve on the samples in the posterior, and you have this KL penalty. And our proposed thing is the same. It's the same. There's just one diff. Let me highlight the diff. Here's the diff. The only difference is instead of taking the average of the likelihood across your posterior samples, we propose that you take the log mean exp of the likelihood across your posterior samples. And that goes from failing to nailing this problem. That one patch allows a misspecified model to go from failing to model the data to modeling the data pretty well. And so that's the kind of content of the work. That's really it. Is the one line change. But in the time that remains, I hope to let's see if we can try to understand what's going on. How can this one change take the model from going from this, a failing of Bayes to a nailing of PACm? What is going on? So, fundamentally, all the inference procedures we talk about, maximum likelihood, Bayesian inference, this PACm thing, they all take the same form. They're all two-step procedures. Step one, you try to find a distribution over parameters. You find some distribution over parameters by minimizing some objective that looks at the likelihood and the data. That's it. You minimize some objective to find a distribution over parameter space. That's step one. You find some distribution over parameters. Step two, you marginalize out that distribution over parameters to form your predictive distribution. Two-step procedure. Find a distribution over parameters, marginalize it out to form a predictive distribution. That's it. And all three of these methods take this form. The only thing that differs is what they use is the loss. So let's talk about that. Let's talk about what loss we should use. Well, what should we use? Well, I mean, if we're targeting prediction, if we're interested in prediction, then what we're interested in is whether our predictive distribution is close to the true distribution. So we would be interested in something like the KL divergence from the true distribution to our predictive distribution. And up to a constant, the entropy of the true distribution, that's this, the cross entropy of the true distribution and our predictive distribution, right? The predictive risk, a measure of how good your model is at predicting is after you do this two-step procedure, you find a distributional parameter space and you marginalize it out, you form this predictive distribution, is to evaluate, on average, for samples from the true distribution, what's the log likelihood of the predictive distribution for those data samples? What's the log predictive probability of those samples? That's the predictive risk. And that's a log of an expectation. Those are kind of hard, right? So what if we, try to bound this thing? What if we bound this thing? We can bound this thing with Jensen's inequality. We can take the log of an expectation, turn it into the expectation of log. And the minus sign, this is an upper bound of this. And this is what we call the inferential risk. Because this is fundamentally a different thing. Whereas the predictive risk was asking, on average, what is the predictive probability we assign to each data point? What is this thing doing? This thing is only ever looking at a single parameter setting, a single parameter value at a time. It's looking at the log of the sort of likelihood for one single setting of the parameters, and it's just doing that on average across draws from the posterior. This is a fundamentally different object. This is a thing which scores single parameter settings in expectation. This is a thing which scores the predictive distribution. And that's the difference. Of course, we can't target either of these. Both of these are out of hand because we don't actually know the true distribution. So what do we actually do in practice? So in practice, for maximum likelihood, their strategy is you just kind of cross your fingers and hope for the best. So you can't take an expectation with respect to the true distribution, so you put a drop-in replacement, you replace the expectation with respect to the true distribution with an average over samples, and you hope for the best. Because this isn't a bound. I mean, this is an approximation. You're going to optimize the approximation. You're going to hope for the best. And, they hope for the best, and it works a lot of the time. Bayesians are not content to cross their fingers and hope for the best. They want some kind of guarantee. And so one way you can tell the story of Bayes is you start with the true inferential risk that we had on this previous slide. You start with this as an objective, and you recognize that we don't have access to the true distribution, but you invoke a PAC bound. And that PAC bound allows you to give a stochastic upper bound on the true inferential risk with this guy, a thing which is the empirical risk plus a sort of KL penalty. And the way I like to interpret this is basically like, it's okay. You can sleep at night. You can assure yourself that you're doing the right thing if you minimize this. And why? Because if you ensure that you don't stray too far from a thing that you guessed before you looked at the data. An honest guess before you looked at the data that wasn't overfit. Kind of more colloquially, I like to say, if you keep one foot inside the door, it's hard to get run over by a truck in the street. As long as you sort of stay tied to a prior, you can't overfit too severely to the empirical distribution. And that's a guarantee. That's a sort of a guarantee that Bayes can give. Because Bayesian inference, the Bayesian posterior, is the objective that is minimized. If you minimize this in the space of all possible Q, you get the true Bayesian posterior. If you do this in some parametric family, you do variational Bayes. But in either case, you can kind of convince yourself that you're targeting a stochastic upper bound on the inferential risk. But the inferential risk, and so that's the point. Fundamentally, Bayesian inference is targeting the best single parameter setting of your model. If you remember nothing else, I want you to remember this. I want you to understand this, that in the status quo, Bayesian inference can be thought of as targeting prediction, but only indirectly. How does it go? What Bayes actually does is it minimizes that sort of PAC inferential risk. That PAC inferential risk was a PAC bound on the true inferential risk. The true inferential risk is a bound by Jensen's inequality on the predictive risk. But it's a two-step process. You're targeting prediction, but only by means of this inferential risk, and the inferential risk was an entirely different beast. Going from P to R involves Jensen's inequality. We swap the log of an expectation for the expectation of a log. And when can we do that? When is that tight? When is the log of an expectation the same as the expectation of a log? Well, it's the same if there's only one point, right? Like if there's a delta function distribution. If your parameter distribution was a delta function, then there's no gap here. It doesn't matter whether you take the expectation inside or outside. If there's only a single point, it's the same thing. That's why, if you have a well-specified... When can you say that the true parameter distribution is a delta function with respect to the true distribution, the true risks? Well, if you have a well-specified model. If you have the correct model, there will be a single parameter setting that is correct, and this bound will be tight. But if you don't have a well-specified model, this won't be tight, and that's the problem. That's the difference. That's why Bayes fails in this case, because it was targeting a thing that was fundamentally looking at one parameter at a time, and for this misspecified case where we have heteroscedastic data but a homoscedastic model, we just can't do it. It's a fail. So how do we do better? Well, we target prediction. Instead of invoking Jensen's inequality, let's target this thing that we care about more directly. Let's try to target the log of the expectation head on. And that's PACm Bayes. Targets the predictions directly. And how do we do it? Masagosa earlier told us about a strategy that he tried. He did a second order Taylor bound on the thing, added a variance term, and was able to target the predictions. We take a different tack. So our tack is, instead of taking one step and going, invoking Jensen's inequality in one step to go from the log of the expectation to the expectation of the log, we're going to invoke a multisample bound. This is just like I-way, you may have heard of in variational Bayes. But you could, instead of going in sort of one step from the log of the expectation to the expectation of the log, you could look at the expectation of the log of an average. And now as the number of samples in your average go to infinity, you kind of get arbitrarily close to the log of the expectation. If you take only a single sample, you get the expectation of the log. And that's really, that's our trick. That's all we did. Let's try to target prediction directly. Let's do it with a multisample bound. And then, if you want the same kind of guarantees that Bayesians have, you turn that into a PAC bound. And that's what we did. So our PACm loss is it ends up looking, just as you might expect. The only difference is now there's a log of an average, an empirical average across samples from the posterior with the KL penalty. And that's why, that's how we got this one line change. But now hopefully you understand that one line change is all the difference. That one line change is what takes us from failing to nailing this one problem. So Please check out the paper. We got other toy examples as well as some larger neural network examples demonstrating that this can scale up to image classification settings. And thank you. Yeah.